So this video is about specific heat capacity. So first of all, the story starts with temperature. Well, we know that temperature is proportional to the average kinetic energy of the molecules in a system. And we know a lot about that because we know that kinetic energy is the energy of motion, and that as the temperature increases, the molecules move faster, which is an increase in kinetic energy. So we're going to transfer from temperature to heat. Now, heat and enthalpy are a little different than temperature. Heat is actually the flow of energy from higher temperature particles to lower temperature particles. Whereas enthalpy is the internal energy of a system. So it takes into account all the energy in a system and also accounts for pressure and volume. Now, a little caveat that under our conditions in the lab, we don't really need to consider pressure and volume because we're not going to be studying the enthalpy of gases. All right, just a quick rundown of energy units. Joules and calories are the most common units for energy. So 4.18 joules is equal to 1 calorie. Those are the most common units that we're going to use in our experiments. 1,000 joules is a kilojoule. These are metric units, so you can use the metric prefixes. 1,000 calories is 1 calorie with a capital C, and the calories with a capital C are the ones that are listed on food packages, which will come in handy in one of our labs when we measure the calories in food. Heat capacity. All right, so here's where we get to the heart of the matter. Now, the specific heat capacity tells you the amount of energy that's required to raise 1 gram of a substance 1 degree Celsius. So, for example, water actually has a pretty high heat capacity. It has a heat capacity of 1 calorie per gram degree Celsius, or 4.18 joules per gram degree Celsius. So I wanted to talk a little bit about substances and relative heat capacity. Well, if you have high heat capacity versus low heat capacity. Well, something with a high heat capacity is going to take a large amount of energy to warm up. It takes a lot of energy to change the temperature of something with a high heat capacity. Whereas something that has a low heat capacity, there will be a noticeable temperature change with very little heat. So something with a high heat capacity heats up very slowly, whereas if it's a low heat capacity, it's going to heat up pretty fast. And the reverse is true. If it's a high heat capacity, it's going to cool down slowly. But if it's low heat capacity, it's going to cool down very quickly. Now, here's the thing about water that makes it so special. Water maintains its temperature better because it has a high heat capacity. Whereas something with a low heat capacity is not going to maintain its conditions. It's going to adjust to the outside conditions very quickly. Here's a few examples. So imagine you're going to compare the heat capacity of the water in this pool versus the air outside. Well, water has a pretty high heat capacity, as I just said, so that the water temperature of the pool is going to stay pretty constant. This is an outdoor pool. It's probably in a really nice area. So that water in the pool is going to take a lot of energy to change temperature. Whereas the air will cool down very quickly when the sun goes down. So the air has a very low heat capacity, and it will fluctuate quickly as you take away the energy. Another example, what about an aluminum pan or a cast iron pan? Well, I have listed there the values of the heat capacity of these two metals. Cast iron has a heat capacity of 0.45 grams per degree Celsius, whereas aluminum, 0.9 joules per gram degree Celsius. Oh my gosh, I messed up the units on the one on the left. So what does that tell you? Well, it tells you that the cast iron pan is going to heat up quicker, but it's also going to cool down quicker. whereas the aluminum pan will maintain its heat. It'll take a little longer to warm up, but it'll maintain its heat better. Okay, so what things affect the heat that's transferred? Well, there's a couple of things that are going to affect heat transfer. One is the heat capacity we were just talking about. The size of the heat capacity was going to determine how much heat will be transferred by a substance. The other thing is the mass of the sample. Obviously, if you have a really large sample, like the amount of water in a swimming pool, it's going to take a lot of energy to heat that. Whereas a very small glass of water, well, you can heat that up in the microwave in 2 minutes. All right, so all of this is summarized by an equation. Delta H equals M times C times delta T. We're going to be using this equation a lot, where delta H represents the energy that's added or removed, which we can call enthalpy. M is the mass of the sample in grams, usually. Cp is the specific heat of the substance, specific heat capacity. Sometimes it's just called specific heat. And then delta T is the change in temperature. So here we have a very quick and easy way to measure the energy of a system, the energy change in the system, by measuring the change in temperature and the mass. Those are all things we can measure. And then the specific heat is a physical property that you can look up. All right, so it's worth noting that a change in temperature, delta T, is always the final temperature minus the initial temperature. So let's just think for a minute about whether you have a positive temperature change or a negative temperature change. So if the temperature increases, the delta T is going to be positive because, so for example, if a substance goes from 15 degrees to 25, the delta T is going to be 25 minus 15, which will be a positive 10 degrees. So the temperature's gone up by 10 degrees. Now, if the temperature decreases, the delta T is going to be negative. All right, so if it goes from 50 degrees to 35 degrees, well, initial temperature is 35, final temperature is 50, which gives us a negative 15 degrees temperature change. All right, that doesn't seem too difficult, but that translates into the delta H, the sign of delta H. So you're going to put energy in, if you're going to increase the temperature, you must put energy into a system. So if you're putting energy into a system, the enthalpy of that system is going to increase. So remember, we're thinking about the energy flow into or out of the system. So if you have a positive delta H, that means heat is, if energy is removed, then the temperature decreases. All right, so the system has a negative delta T and therefore has a negative delta H. So heat is being removed from the system. Okay, so the positive or negative sign shows you the flow of heat in the system. All right, so here's an example. Now here's a few problems to show you how to use this equation, the enthalpy equation. So we have the equation here, delta H is equal to M times C times delta T. All right, so in this first problem, we're adding heat to the system. So we have a positive delta H. So the first thing I'm going to do is define my variables. You can make a delta by doing escape, capital D, escape, if you want to get all fancy. So our delta H in this case is positive because we're adding heat to the system. The mass of our sample is 45 grams. Is anybody happy that we don't have to use the mole yet? It's coming. Now, our delta T, now in this case, we're actually trying to find the final temperature. So we need to actually break this down a little because we know delta T is the final minus initial. So we know that the initial temperature is equal to 25 degrees Celsius. Now, if we're putting heat into the system, we're going to expect an increase in temperature, right? Temperature should go up. All right, we need one more variable, the specific heat of water, which is C. joules per gram degrees Celsius. All right, now, so here's my equation. Why don't I just copy it? And we're going to use the solve function with one little change. Whoa, what was that? We need a double equal sign. So delta H is equal to MC delta T. But in this case, we need to break down that delta T because we actually want to find out what the final temperature is. And we know final temperature minus initial temperature. So it's TF minus TI. And we're solving for the final temperature, which I'm calling TF in this case. Okay, now if we have this all set up correctly, we should get an answer here. What did I do wrong? Oh, I need to close my parentheses. There we go. And I need to input my variables. All right, and indeed, our calculation matches our prediction. The temperature went up. 2 significant digits in our answer, 27 degrees Celsius. Okay, so here we have to assign the variables and solve the problem. All right, so let's try the next one. I'm just going to go up here and clear my variables out again. In the next example, we want to calculate the energy. So we're looking for delta H this time. We know the mass of the sample, we know the change in temperature of the water, and we know the specific heat of water. Okay, so this is pretty straightforward. We're going to just define our variables. M is 25 grams. That's the mass of the substance. Delta T, well, why don't we go ahead and put it in there as delta T this time. Delta T, well, it's the final minus initial. The temperature is going down, so it's the final temperature is 30. The initial temperature is 75. And I'm going to put that in parentheses, oops, and put my units on the outside. Okay, and what else do we know? We know the specific heat of water, 4.18. Actually, I'm just going to copy that from up here because that's the same. Okay, put that right there. And we're solving for delta H this time. Go back up here and grab my equation. If you're solving for the variable on the right, on the left, you don't really have to use the solve function. So let's see if it works. There we go. There's our heat. We have to remove 4,702 joules. Well, we should round that to correct significant digits. Our final answer, 4,700 joules, or 4.7 kilojoules. Okay, it's not that hard. Just think about your substance, think about the variables that you have, and plug them in. The only tricky part is if you have to break down delta T into final minus initial. I'll leave the last one for you to try on your own.